critically important that we understand how IP addressing works. Whether you're on Facebook or analyzing a malicious command and control server, they're all going to use IP addresses to communicate from one point to the next. Our ability to understand this addressing schema, how it supports communication from one or one-to-many hosts, will allow us to understand and characterize networks so that we can be more efficient in how we scope, remediate, and even do consulting or analysis work to support our own organization's security goals, whether that be offensive or defensive in nature. So let's start by talking about the Internet Protocol version 4. It's one of the two major versions that are in use today. IPv4 is the older model. We have IP version 6 that is newer, but still about 10 years old. And IP version 4 can be characterized as a 32-bit string. What this means is that it's comprised of 32 ones and or zeros, which make up the overall value that is used to identify a IP version 4 address. So a router, a computer, an endpoint device, they all can read this 32-bit string of ones and zeros and then convert that into a logical address so that they can know how to communicate or where to send their packets to. Because it's binary or base 2, if you take 2 to the 32nd, you come out with roughly 4.29 billion addresses, and that's how many total available addresses exist within the IP version 4 schema. When the creators of IP version 4 realized it and made it public, they never thought that we would run out of IP addresses. And as of roughly, I think it was March 2013, we had fully exhausted all available IP version 4. There's many organizations that have available IP version 4 addressing. They've been leasing it out for top dollar. But that has also paved way for the expansion of IP version 6, which we'll talk about a little bit later. So we talked about how routers and computers read these binary strings, and here's an example of what a base 2 IP version 4 address looks like. Here we have 4 octets, or 4 groups of 8 bits of either ones or zeros, and this makes up the 32-bit string that is an IP version 4 address. We can see the base 10 version, which is the typical numbering schema that we use when we count 1 through 9 to include 0. And that binary string, when converted to base 10, comes out to 10.11.12.13. That is the IP address in base 10, and that is the IP address in base 2 binary. So it's just something interesting to note that everything your computer does, you're listening to my voice, you're watching this video, you're looking at these slides, all of that is simply ones and zeros that is being computed and calculated by your computer at billions of times a second. So no matter how simple the task you do on your computer or how complex, it all can be broken down to either a 1 or a 0. And something else we want to consider, we should think about ones and zeros in the computing world as true or false or on or off. A 1 is true or on, and a 0 is false or off. This will be very important later when we start calculating or converting binary. So as we talked about, IP version 4 has all but since been exhausted as far as the total available that are still available to be sold or leased to new organizations. So before that occurred, the organization that manages and released the IP version 4 standard realized that we had to create these blocks or defined ranges to better or more efficiently allocate their use, right? We wanted to create small manageable blocks to very large manageable blocks depending on the organization's need so that we can give it to them instead of people just sort of carving and slicing and getting random sets of IPs. We wanted to do it in a more logical way. So they created these ranges or classes of IP addresses. So there's 3 primary classes that we deal with day in, day out, but there's 5 in total. So let's talk about those. So a class A network represents the largest size network you could have. So if you look at all the available IP addresses that exist in the world and you broke them into class A sized ranges, it would be represented in the IP address 1.0.0.1 through 126.255.255.254. That is the range from beginning to end that make up all the Class A ranges. Now, out of those ranges, you have 127 unique networks, and each of those networks have 16 million hosts each. So as you'd imagine, that's a lot of hosts, but 127, that's not a lot of networks to give out. I know the US government has, I believe, 2 for sure, and I think they probably have a third one. But you'd imagine that not every country has a Class A range. Xerox, one of the founders and core research and development arms of the early protocols in internet, they have a Class A range, and many of the other early adopters of the internet bought into these larger class ranges, and they're the ones who are making really good pretty penny right now because they're reselling a lot of these IP addresses to smaller organizations. We then have Class B ranges, which go from 128.1.0.1 through 191.255.255.254. And out of that range of addresses, we have 16,000 unique networks, so a whole lot more than a Class A, but with only 65,000 hosts each. But as you imagine, that's a very large network, 65,000 unique hosts. That's a whole lot of devices. So there's still not many organizations that can satisfy or use a whole Class B range of addressing. And then last but not least, the Class C range, which starts from 192.0.0.0 through 223.255.255.254. So this is the smallest of the more common network we might see in use, and it has 2 million unique networks with only 254 hosts each on each of those networks. More than likely, your home network is a Class C. A lot of you will have a router that starts with 192.168.1.1. That is a private IP address, and we'll talk about private IP address ranges in a moment. But that is a small network that only has 254 usable hosts in your network. And then we have Class D and E. The Class D range is used for multicast, which we're going to dive in a little bit more in a moment, and Class E, which is used for experimental and future use cases. In total, there are roughly 2,016,127 networks. So that's really not a lot of networks when you think and compare that to the needs of the internet. We only have 4.29 billion addresses, but that's distributed across 2 million networks. So that's very inefficient from an IP address allocation. So there needed to be new ways to slow the exhaustion of IP addresses as they were being given out, and we did that with private addressing. So a solution to the rapid decline in available IP addressing that was available to be doled out to businesses and governments was the creation of the RFC 1918, which stands for Request for Comment 1918. And in this RFC, it was declared that there would be certain ranges in each of the classes that were earmarked solely for private communications. And the point of this being is that these private IP addresses could not be routable on the internet. You cannot take your private IP address from your computer and try to talk to a public router. That router, if you could get an IP address out there, the router would just drop that packet. It would never make its way beyond that first router. And that way we ensure our private addressing is maintained inside the network. And what is the benefit of that? That means we can reuse these IP addresses over and over and over. And like I mentioned earlier, more than likely many of you have a home IP address that begins with 192.168.1.1 through, any number of IPs that are modified for the number of devices you have in your network. But every house on your street can have the exact same private IP, and it does not affect any one of you. However, if everybody tried to use the same public IP, you would lose internet connectivity, packets would be dropped, stuff wouldn't get routed appropriately. So that was the problem that we were dealing with, not the fact that multiple public IPs were giving out, it's just that there wasn't enough public IPs to give everybody and all of their devices. So we carved out these ranges to create unique private IP addresses so that they can be reused internally and free up a whole bunch of IP addresses for public use. So we have the Class A private range at 10.0.0.0 through 10.255.255.255. Another way to remember this is if any IP address you ever come across starts with a 10, it is a private IP address. You don't even need to remember the other addresses. If it's a 10, it's private. And a Class A private range consists of one unique network with a total available number of hosts at 16.777 million. So one Class A private range can have many, many hosts. And the benefit is we've given up one of those 127 private addresses, but now this network can be reused an infinite amount of times, whereas we previously only had 127 Class A addresses. Only 127 networks could be that size. Now with this private address, we can have an unlimited number of private Class A ranges of that size. Next, we have the Class B private range, which starts at 172.16.0.0 through 172.31.255.255. And one way to remember this is just simply remember 172.16 through 172.31. If you can remember anything starting with 10 or 172.16 through 172.31, you now have memorized the Class A and B private addresses, and the benefit being is you can quickly identify if any IP you're shown is from Class A or B is public or private. So last but not least, Class C private range is 192.168.0.0 through 192.168.255.255. It's critical that you understand the difference between private and public addressing. Private addresses are strictly used for internal network communications, and public addressing is used for internet-bound public communications. So when we're reviewing logs or analyzing alerts from a system, it's very critical that you can determine the difference between the two just by sight alone. And the easiest way to do that, like I said previously, is to simply remember the ranges of Class A, B, and C private addresses. So anything starts with a 10, it's private. Anything that's 172.16 through 172.31, private. If it's 192.168, it's more than likely private. So just remembering those three little ranges, you can quickly be able to identify out of all 4.29 billion addresses, which ones are public and which ones are private. Now that we understand what IPv4 addresses look like, their classes, public versus private ranges, let's talk about the different types of uses of IPv4. So the most common most people might be familiar with is unicast. This is when we use our IP address on our computer or device to talk to another specific computer or endpoint on the network. This is a point-to-point communication where we send data from one device to the next. The next use or IP that can be used in a network is a broadcast IP. This is an IP address that when used, it's basically like an all-net broadcast where we want to notify all hosts on our local network of some new information that we want to share. When a new host enters the network, it might use a broadcast to notify all machines on the local network of its presence. So similar to broadcasts, a multicast is a type of announcement on a local network. However, the difference being that devices that are subscribed and listening for these multicast addressing will only respond to those events. So a good way to think about what is a multicast addressing schema used for, if you've ever turned on an Xbox, a game system, a TV, and you've used media sharing where your TV or gaming console can see another device and stream media from that device, that is multicasting. That is one of those devices is doing a multicast address saying, hey, I'm a media server and I want to share media on this network. So any other device that is listening for that multicast address can respond and say, hey, I'm interested in that media. I'd like to stream from you. So that multicast address is how that device broadcasts what type of service it is, but it's multicast in the sense that only the devices that are interested in that service will listen to and respond to that communication. So let's break down and dive into an IPv4 header. This is the schema of what is actually sent on the wire. And remember that an IPv4 address is 32 bits, and the overall header is 32 bits in length. So each one of these lines represents 32 bits sent over and over to go through this header. So think of almost like you're reading a document or a typewriter. We're going to do left to right. We're going to get to 32 bits, and we're going to hit the return key and go to the next line, and we're going to read all the way to 32 bits and keep going on through. And this is essentially what our computers do. Every time they get 32 bits, they try to compile those bits into these fields to make sense of them, and then they listen, of course, for the next 32 bits, so on and so forth, until they process the whole length of the header to understand what information is coming in the network interface. So the first field of interest is the version field. This denotes what version of IP protocol we're using, and of course in this instance we're using version 4. The header length provides the overall header from the first bit to the last bit in the overall length of this header, or how big this header is. That way the computer that begins receiving this data knows how to slice and dice these bits into these fields so it can properly read them, so it can apply it to a known protocol schema, the IPv4 schema, and understand what the ones and zeros mean, because if it doesn't understand where the header starts and stops, it can't align the ones and zeros in any logical order that makes sense for this protocol. The type of service field is used for somewhat quality of service. It informs the router how to process this packet based on priority, and over the years it's been modified and used for various means, but in general respects it's used for quality of service and prioritization of packet processing. The total length is the total header and payload length. So we started in the second field there with the header length, and that helps the device understand where the beginning and end of the header exists, but we also need to know the total length from the beginning of the header to the end of the payload so that the computer understands all the bits it needs to process for this one packet. We have the identification field, or the IP ID field. This is used when packets are fragmented, meaning that there's too much data to fit in one singular packet, so the data is fragmented across multiple packets, and the IP ID is a unique number sequence that's used by receiving devices to resequence or put the files or packets back together in the right order. Next, we have the flags field. This is simply where certain bits are turned on or off to represent various flags. And we'll learn more about flags when we get into Wireshark and analyzing some of these headers. Fragment offset is also used for fragmentation. It provides the offset of the bytes so that it can assist in reproduction or reproducing the collected packets. Time to live is used to decrement a counter each time this packet is processed by a router, and the default is 32 hops. And that is done so to ensure that any given packet on the internet cannot just sort of exist in eternity, where you'd have these packets that don't have a real destination and they would just be bouncing around on the internet. So what a time to live specifies is once this packet has been processed by 32 routers on the internet, it will not go to a 33rd. The packet will just be dropped on the floor. The protocol specifies if this is a TCP, a UDP packet, or ICMP packet. Next, we have the header checksum. This is a calculated value that are used by routers to check the integrity of a received header. If the calculated value the router assesses is different than the header checksum that's in the packet, it determines that the packet has been corrupted during transmission and will then communicate to the last router or device to request that that packet is resent. This way we ensure the integrity of delivery of these packets across the internet. We then have the source address, or the IP address of the device sending this packet. We then have the destination address, or where is this IP packet going to? And then we have the options field, which is used for a number of things from security, research, things of that nature. It's not always used. It's very rare sometimes in various networks to see an option header. And in many organizations, they actually configure their routers and various devices to trim off the options header. And if an option header is used, you require the additional padding there to make up a full 32-bit string, because remember, it needs 32 bits equally so it knows where it is in the header in relation to the payload. So if there is no options header field, there won't be any padding. It will just end at destination address and go right into the payload. And the payload is the actual data being sent. So one way to think of this, and bringing back up the concept of encapsulation, if the protocol field states that this IP packet has a TCP protocol in play, the payload will be a TCP header followed by the payload in that TCP packet. So we'll have an IP packet, so think of a larger envelope. On the outside it says, hey, we're going to this destination address and here's my source address, and this is a TCP packet envelope. And on the inside will be the TCP header and the payload that is inside that TCP packet. So a packet in a packet. And that's essentially what encapsulation is, and how we encapsulate these protocols to get data from one network to the next.